Hi everyone, good day, and I hope you all are well. So we are looking at the last section of chapter 4, and we are going to start chapter 5 after this last section. So in the last section of chapter 4, we are talking about Heidegger's equation of state. So let's look at the keywords. So we may have to interpolate if there is a need for interpolation. We have to talk about temperature. We have to talk about temperature, which is capital T. We have to talk about specific volume, which is small v. We have to talk about volume, which is capital V. We have to talk about vapor, which is just a substance. We have to talk about water, which is a substance. And we have to talk about the property table, which you all know we use to get the different property. And linear interpolation, we may need to look at that in case we don't see the property which we are looking for. And we have to talk about pressure, which is capital P, and mass, which is m, small m to be precise, small m, because capital N is molar mass. So now the Heidegger's law. The Heidegger's law is used to define a system which has a constant pressure, a constant volume, and a constant temperature. So, but in this context, remember, we are saying that the pressure for the system has not been iterated. The pressure has not been changed. The pressure is kept constant, and therefore, if a pressure is kept constant, then that system is said to be in an ideal state. So we call that system an ideal equation of state. And in that, you want to say that the pressure is kept constant, the specific volume is kept constant, and then we have R, which is the ideal gas constant, and T is the temperature. So the equation of state can be written in this form. Pressure, specific volume is equal to what? Is equal to ideal gas constant times T. So this is what we call the ideal gas equation. And that equation is what you are going to see. So it is the ideal gas equation. And these are the different forms in which the equation can be written. So make no mistake, like I said, the pressure must be constant, the specific volume is constant, the temperature is constant, but it's actually an assumption of principle, because if the pressure increases, the temperature is going to increase, and if the pressure increases, the temperature rises. The equation is likely not going to be an ideal equation of state, because when the pressure rises, the temperature rises. Like case 2. Case 2 may not be an equation of state system. Sometimes it is really confusing to make a conclusion. If this pressure gets to be to about 1 megapascal, it is definitely not an equation of state. So this formula cannot be applicable. But in this case, the only way we can determine this is to be able to calculate the error. And if the error percentage is less than 1%, then that system is an equation of state system. So the error analysis is what helps us to know. So when you are asked, is water an ideal equation, an ideal gas equation? It could be yes, it could be no, depending on the pressure. But if the pressure of water goes above 1 megapascal, it is no longer an ideal gas equation of system, and therefore we cannot apply that ideal gas equation in that system. So that is what you should know. And if you come below, you can clearly see what I'm talking about here. Every system that has a percentage of error which is less than 1%, that system is an ideal gas system. Therefore, the ideal gas equation is applicable for this system. And how do you determine such system? We say the specific volume for the table minus this ID specific volume divided by the specific volume for the table times 100. If this answer is equals to less than 1%, then this is a system that we can say the system is ideal gas system. Remember, this V at the specific volume. And therefore, look at this graph, and you could tell that 1 megapascal can be an ideal gas equation, can satisfy the principle of ideal gas equation as long as the percentage error is less than 1. 100 kilopascal will likely be as long as the percentage error is less than 1. 10 kilopascal in all cases is an ideal gas system because the error factor will be less than 1%. And 0.8 kilopascal is an ideal gas system because the percentage error is less than 1. So in conclusion, to make a determination of an ideal gas equation for maybe you want to compare the propane you buy in Walmart, the gas you buy in Walmart, or any substance which you are dealing with, to be able to determine if that substance is an ideal gas system or that substance satisfies the ideal gas equation principle, you must determine the percentage error and make sure it is less than 1%. But if it is not less than 1%, it doesn't satisfy that principle. So it's some kind of a logic or an abstract way of thinking, but we need to make a conclusion only on the percentage error. So if you are asked, is water an ideal gas? Satisfy ideal gas condition? The answer can be yes, the answer can be no. It all depends on the percentage error. That's what I'm trying to emphasize here. So now, look at the different formula which you have to understand. We have P, which you all know is the pressure. This small v is the specific volume, arrow, ID, gas, constant, and T is the temperature. Now remember, we have different value for ID gas constant for different systems. For air, for helium, for nitrogen, we have different values, so make no mistake. Now, if you are asked to calculate the ID gas constant and you are given the universal gas constant and you are given which is actually RU, and you are given the molar mass, which is actually M. So if you are given the molar mass and the universal gas constant, you can determine the value for ID gas by dividing the universal gas constant over the molar mass. So in the case you want to determine the mass, this small m is the mass. Well, you can determine the mass if you have the molar mass and the number of mole. So if you have the number of mole and the molar mass, you can determine the mass of quantity of fluid or substance. Now, let us proceed. In a situation whereby I want to calculate the volume of fluid, capital V. If I know the mass and the specific volume, I can determine the volume of fluid. If I know the pressure, I know the mass, I know the ideal gas constant, and I know the temperature, I could determine the volume as well. Vice versa, if I know the mass, the molar mass and the number of mole, and I know the ideal gas constant, I can determine the mass. In a way that if the problem changes and you have the universal gas constant, you have the value for N, which we know is the number of mole, you can still determine any of the value. If you have the pressure, the volume, the number of mole, the universal gas constant, and the temperature, you could determine the volume as well. So if you have the molar specific volume, which is V, small v, and this bar on top, you may determine the pressure when you know the universal gas constant and the temperature. So these are the different formula which you can use to calculate the different value. So now, when I have two systems that are kept fixed and they satisfy the ideal gas constant, I have at point 1 and I have at point 2, I have a tank and a tank. This I have P1, this is V1, this is T1, this is P2, V2, and T2. I can say P1 equals to V1 over T1 equal to P2 over V2 over T2. I may solve for either V1 or V2 or T1 or T2. So when you have 2 points of contact that connect to each other, that satisfy the ideal gas equation, that can be useful to determine 2 unknown values. So now I'll stop the video and then I'll do compressibility factor and then I'll solve some problem. Thank you all.